Our next presenter is Taryn Gibbs, a doctoral student in nuclear engineering. Her presentation is titled Nuclear, the Recyclable Energy. Please join me in welcoming Taryn to the stage.
Science has determined that in order to preserve a livable planet, global temperature increase must be limited to 1.5 degrees C above pre-industrial levels. Today, we are only 0.3 degrees away. A global effort has begun to achieve net zero carbon emissions by 2050. Scientists have determined that this achievement might be enough to reverse global warming and avoid the worst impacts of climate change. But it will require nothing short of a complete transformation of our energy systems. Currently, we rely on fossil fuels and some renewables like solar, hydro, and wind. But even these can do more harm than good. Nuclear power is cleaner and safer than fossil fuels, more energy dense and reliable than solar, and less expensive and wasteful than wind. It's easy to see that nuclear power is cleaner than fossil fuels, but it's safer too. Did you know that fossil fuels release 10 times more radiation into the environment than nuclear power plants? In the form of coal ash released directly into the environment. Perhaps the biggest difference between nuclear and renewables is their energy density. Taking into account land for construction, resource mining, and waste handling, it would take 60 times more land for solar and 400 times more land for wind power to produce the same amount of electricity as one nuclear power plant. I'm a Ph.D. student in the Alchemy Lab, a diverse group in the School of Nuclear Science and Engineering, aiming to advance nuclear technology with better fuels, better data, and my specialty, better separations. With my research, I'm hoping to make nuclear technology even safer and more sustainable, so that as a nation, we can decarbonize and reduce our climate impact. You don't need to know everything about nuclear reprocessing, but the first thing you need to know is that spent nuclear fuel isn't spent. After 5 years in a reactor, only 5% of the fissile material has been used. At this point, however, the buildup of fission products has lowered the efficiency of the fuel, and it must be removed from the reactor. The second thing you need to know about spent nuclear fuel is that it's a chemically complex material. Fission products account for 50% of naturally occurring elements, all behaving differently in the fuel. On top of that, neutron activation of non-fissile uranium has led to the buildup of plutonium, which must be managed accordingly to prevent weaponization. The historical approach to this is depicted here. This is the Purex process. It's a two-phase process like mixing oil and water that was developed in the 1940s by the United States to produce pure uranium and plutonium for nuclear weapons. It works like a claw machine, using an extractant to grab uranium and pull it into the organic phase, thus separating it from the bulk waste. This had many problems, though. The most alarming being the production of large amounts of radioactive, highly acidic waste, and the use of chemically unstable compounds which decompose into explosive oils. Additionally, this process was designed to produce nuclear weapons, but the United States and 189 other countries agreed in 1968 to halt their production with the Nuclear Non-Proliferation Treaty. All these reasons make the Purex process highly undesirable. My challenge, then, is to make reprocessing cleaner, safer, and proliferation resistant. What we're going to go through next is the recipe that I follow for my proposed separation method. A recipe for recycled nuclear fuel. To start, I use some very expensive equipment. The Oregon State University TRIGA reactor produces no electricity, but a hardy stock of neutrons, which I use to make materials radioactive. Actual spent nuclear fuel is a controlled material, so I make my own in the lab from scratch. I pass materials through the reactor, and they come out looking exactly the same. But now I can track their movement throughout my separation by following their characteristic radiation signature. Next, I bake the simulated spent fuel, which transforms the uranium into a beautiful green crystalline form called ammonium octafluorouranate. This is then dissolved up, while most of the fission products remain as solids. I then filter this mix to separate the uranium from the undissolved material, and then to further purify my uranium product, I regrow the crystalline material by adding an anti-solvent, like methanol, to reduce its solubility. Once precipitated, I filter off the remaining liquid and voila, uranium, recycled and ready to be used as nuclear fuel. My experimentation is still in its early stages, but already I've had promising results. To date, I've recovered more than 90% of my uranium starting material, while also removing up to 100% of some simulated fission products, many of them greater than 90%. Today, we've explored the power of nuclear in achieving net zero by 2050, discussed the history of nuclear reprocessing and its challenges, and of course, learned a new recipe for safe and effective recycling of nuclear waste. I hope you're all as excited for the future as I am, as we move to harness nuclear power to combat climate change and advance peace for all. Thank you.